All right, now let's take a look at the nervous tunic. Now the nervous tunic is the innermost layer here, shown in yellow. All of this is also the nervous tunic. So the nervous tunic is really the retina. So the retina is the inner layer of the eye wall that contains photoreceptors. It is continuous with the optic nerve. So there's the optic nerve, so it's continuous with that. A couple of structures on here. I think I gotta move ahead on some pictures, so we'll get to this picture here. So one is the macula lutea. So right there is the macula lutea. So I know macula, I told you, means spot. Lutea means yellow, literally means yellow spot. So this is a yellow spot in the central region of the retina. And within that is what is known as the fovea controls. And this is a depression in the center of the macula lutea. And this is where we have our sharpest vision. So, you know, if like you're reading a book, you know, the light rays are hitting right at your fovea controls. Right over here is the optic disc. Now the optic disc is an area where nerve fibers leave the retina and join the optic nerve. In fact, we don't have any photoreceptors, the receptors that sense light there, all right? So we actually have a little blind spot in each of our eyes. Now you don't really notice it because the peripheral vision of your other eye can see in that area. Okay, so let's go back to this picture here and look at cavities in the eye. So the lens is the divider. So everything in front of the lens is the anterior cavity, everything behind the lens is the posterior cavity. So the anterior cavity is the cavity in the front of the lens, and it contains aqueous humor, all right? Next is posterior cavities, so that's everything behind the lens. So there's a cavity of the eye behind the lens. And this is filled with a different kind of fluid called vitreous humor, so gelatinous fluid. So it's a transparent jelly-like fluid within the posterior cavity. So they're showing right there, that's that vitreous humor there. This helps maintain the shape of the eye. It also transmits light rays as well. Let's look at the physiology of vision. So the physiology of vision is based upon refraction. So light changes speed when it moves from one type of medium to another type of medium. So from air to a solid or from air to a liquid, all right? So the less dense it is, the light speeds up. The more dense, like glass, it's gonna slow it down. And when it slows down, that light gets bent. And this is what is known as refraction. Refraction is a bending of light rays through a medium, all right? So what a lens does then is it bends those light rays. So our lens is a convex lens. So with a convex lens, so let's just go to this picture here. This is showing a convex lens, and what a convex lens does is it brings those light rays to a point, which is known as a focal point, okay? And so whatever started up here on top ends up on the bottom. Whatever was on the bottom now ends up on the top there, okay? So another kind of lens is what we see here, and this is called a concave lens. And when light rays go into a concave lens, it causes light rays to diverge. So if the eye wasn't here, these light rays would continue to diverge out. There would be no focal point there. So as I said, our lens is convex, and so the image that forms on our retina is upside down and backwards, and our brain readjusts that image. So if we look at types of vision, in normal vision, also known as emmetropia, here the focal point is on the retina. It's actually a little bit before the retina, but it occurs so you get a nice image on your retina. In myopia, nearsightedness, the focal point is before the retina. So here it occurs way too soon. So here, because it occurs way too soon, we get a distorted image on our retina. So here the eye is too short for the lens that it has, all right? And so one of the things is why you're nearsighted, why you can see things close, is your lens flattens for that close vision, so it allows you to see there. But the thing is that our lens is supposed to flatten for distant vision, so it can't, it can't flatten anymore for that distant vision. So you can't see out there. This is corrected by concave lenses, so they spread those light rays out before they enter your eye. This works on glasses. This is also the same physics that works with contacts. So it's harder to see with contacts, but they're going to be thicker on the edges than in the middle. Next is hyperopia. or farsighted. Here the focal point is behind the retina, so it occurs too late. And so once again we get a distorted image, and so that's why you get the blurry vision. So here the eye is too short for the lens that you have. So you know what happens here, why they can see far away and why they can't see up close, or why they can see far away and not up close, is that lens thickens for that distant vision, and that allows them to see that distant vision. But once again, this is not what we're supposed to happen. It's supposed to thicken for close vision. And so because it's already thickening for that distant vision, it can't thicken more for that close vision. And so that's what happens. Once again, this is corrected with actually a convex lens, which causes the light rays to come in sooner. And so you get that image forming on the retina at the right location. Okay. Let's look at the different types of photoreceptors. Now, photoreceptors are receptors that sense light. We have about 250 million photoreceptors in our eye. Vision is our most dominant sense. So there are two types, and they're named kind of for their shapes. This is rods here, and these are cones. Okay? So rods detect dim light and peripheral vision. They are more numerous, and they are more sensitive to light, so they have a lower threshold. Right? The problem with them is they don't provide sharp images or color vision. Now I'm going to explain that here in a second. Now cones, these other ones, these operate in bright light and provide color vision. All right? So they give us the sharper vision there. So if you're in a, like you wake up early in the morning and you're in a darkened room, you might notice you're not seeing colors and things look a little fuzzy, and that's because you're using those rods. All right? And so when we turn the lights on, now we have a lot of light available. Now those cones start firing, and you can see all the colors, and you can see sharp vision there. All right. So we have three different types of cones for detecting the different colors that are out in the visual spectrum. So if we take white light, we pass it through a prism, it's going to bend that white light into all the different colors of the spectrum here. And so this is showing where each one activates. Now, there are two variations for the red cone. Now, people who are red-green colorblind, they're missing one of these two cones, and so they can't distinguish between red and green colors. All right, and so this is showing a plate, and if you're red-green colorblind, you would see 28 here and 52 over here. And I'm totally joking. You should see 74 and 5 if you have regular vision.